There is one shorthand notation which I will ask you to recall. This, if you notice this FEM, this whole term over here, it becomes very tedious to write again and again. So I've called it this capital phi. We had done this earlier also. Okay, so this phi, when you see, is just this integrand. Okay. So now what we are going to do is, let's take a object is over here. Let's take my one triangle on the boundary. Okay. So this is my n hat, outward normal, and I am just going to number these edges as 1, 2 and 3 for simplicity. Okay. So in the FEM, what did I do? In the traditional FEM, I basically cycled through all different possible values of these testing functions. I took the testing function to be each one of these edges, and I wrote down my system of equations. Okay. And since there are n plus m edges, there are n plus m testing functions. So we are familiar with all of that, but now let's look at that equation which will get altered by what we have done, and that will happen when my Tm is on the boundary. Okay. A boundary edge is what is going to invoke this right hand side. That's, otherwise Tm is 0 on the boundary, right? If m is not on the boundary, if this m is not on the boundary, this term is 0. Bad choice of variables. M here is supposed to be variable, but we made it equal to number of boundary edges, but hopefully it's clear. You can make this all into I if you want. Okay. Okay. So what is the magnetic field expressed as? We already know this. This is going to be written as sum of ui ti, right? I is equal to 1 to 3. Okay. So my FEM equations are going to give me, I am going to choose a testing function, right? So I am going to choose T1 as testing function and generate one row of my matrix equation from FEM, only one row. Okay. So what will happen? So integral over this triangle is going to be phi of T1 comma h d2r, right? I mean, d2r is the surface differential element. So if you want, you can just call it dr. Okay. And h is going to get replaced from here. Okay. So what will this? How many terms will you get over here? H will write in terms of T1, T2, T3, right? So this is going to become. So h when I write as u1 T1 plus u2 T2 plus u3 T3, right? U being a constant, this will pop out. So I'll get u1 integral of capital phi of T1 T1, okay, dr plus u2, same thing will happen, capital phi of T1 T2 u3, capital phi of T1 T3. You notice this guy is, it's linear in h. If I replace h by h1 plus h2, it will just become capital phi of the sum of those two terms. Right? So this is where I am getting my this row will only involve u1, u2, u3 and no other edges of the entire formulation. That's why it is sparse, right? And now this is going to be equal to what? The boundary term, which by our careful thing over here is going to be this term, right? So it's going to be plus minus j omega naught L1 times Ez, right? So for Ez, let me write it over here. This Ez of r, okay, I am going to write in terms of the pulse basis function, right? So I can write I is equal to 1 to m, because there are m of them, some ai unknowns, and pulse basis pi of r. Okay, so this is my along the boundary. Yeah, Ez is discretized along the boundary only. Yeah. So this is going to be plus minus j omega naught L1 multiplied by, you notice I need a Ez over here. So what value of Ez will come? A what? Remember, this is one boundary, one edge along the boundary, right? And then there is going to be another edge, and then there is going to be another edge. Like this, there are how many such edges? M edges, right? And the pulse basis function is 1 along each edge, right? So over here, this is going to be basically A1 if the numbering begins from here, if this is also edge 1, right? So let's call this edge 1. I am replacing Ti by T1. I am calling that 1 to be the first edge. Okay. So you can imagine there is some bookkeeping to be little bit careful about how you are numbering things. Okay. Fine. So what kind of sort of system of equations have I got now? So if I just do the FEM system of equations, I will have how many equations? I can test along each of the boundaries, I mean each of the edges. So n plus m equations, right? But in m of those equations, right? So I will have n plus m equations total from. Yeah, we are coming to the boundary conditions. Okay, n of them are interior, so they do not involve the AIs, obviously. Okay, m of them involve AI. Okay, but our number of variables in this problem has become how much now? If I am going to use this equation 5 over here, my number of unknowns has now become n plus 2m. So it's going to be n plus m plus m. So what are these? These are h tan, and what is this? Ez. So I am making my system of equations a little bit larger, right? And the FEM equations are going to involve this Ez fellows, right? And what happens to, I mean, there are not enough equations right now. I only have n plus m equations, whereas the number of unknowns is n plus 2m. But I know that if I use equation 5 over here, I am going to get another m equations. So what will the BI equations look like? The BI equations, the boundary integral equations, involve what and what? So for example, when I take equation 5, there is Ez and there is h tan. H tan is related to, no, h tan is related to use. H tan is use, and Ez is, right? So if I write this out into a matrix equation, what will I get? I am going to get something of the following. So Q, let's call it, so APQ, some matrix APQ which has all the terms inside it, times UQ plus some matrix B times my small aq. Actually, you know what, instead of calling this A, let's just call it V, so that there is no confusion between lowercase a and uppercase a. Okay. So the coefficients in the pulse basis for the electric field I am calling V. Fine, let's just change it from small a. Say again. V? V1, yeah, correct. Very good. Okay, so this is the equation, and what is the right hand side going to be equal to? It's going to be equal to this guy, incident field. So I am going to call that E of P. Q is allowed to run over gamma, the boundary. Okay. So, this is m equations in total, and most importantly what has happened is the information about the electric field, the incident electric field has nicely appeared over here. So, now do I have enough equations? If I combine, so combine this one and this 2, how many unknowns do I have? N plus m plus m? In the total problem has a interior discretization as well as boundary discretization. Interior discretization has n edges, and those unknowns continue to be unknown, they are not determined. So, those are those n. On the boundary I have my hz and etan both are undetermined. So, how many unknowns are there? N plus 2m. How many equations do I have in total with me now? N plus m from FEM, m from boundary integral. So, I have actually managed to merge these two in a very clever way.